Effects of post-processing photopolymer 3D printer resin with UV light on IZOD impact strength by John Bingle, Aidan Dempsey, Daniel Greco, and Benjamin Tobin. So
Yeah.
you may be wondering, what is photopolymer resin and how is it used in 3D printing? Photopolymer resin is cured in a plastic-like substance when exposed to UV light. This type of resin is commonly used in mass stereolithography or MSLA 3D printing. The printers work by curing a layer of resin together into solid parts using UV light, which can be seen in the center picture. With enough layers stacked together, a solid part is made. Once the part is removed from the printer, it must be cured with UV light and heat. This post-processing makes the part more rigid, gives it greater tensile strength, and decreases handling risks. Post-processing is done in a cure station, which can be seen on the far right picture. The overall goal of our experiment was to determine what effects does cure time have on impact strength of different resins, and is there an ideal strength or ideal cure time for each resin tested. To test impact strengths, we created an IZOD test stand in accordance with a specific standard. Test specimens were printed to the same standard in 3 different resins and cured for different durations of time. As resin printing technology has advanced, it has become more popular. Resin printing allows for greater dimensional accuracy than traditional fused model deposition 3D printers. However, not a lot of research has been done on the impact resistance of resins and how different cure times impact a part's IZOD number. In fact, we couldn't find IZOD numbers for one of the resins we used. Since most of us work in the makerspace, we can use the data collected to make better suggestions to researchers on which resins and cure times to use if impact resistance is essential. Background. We constructed an IZOD test stand and test samples to the ASTM D25610 standard. IZOD testing works by using a pendulum with a hammer to break test samples made in accordance with the standard. The hammer is released at the same height every time, and using physics and trigonometry, the impact energy can be calculated. Before the experiment, we only had data for Formlabs resins. For Formlabs black, clear, and white, the average impact energy is 16 joules per meter uncured and 25 joules per meter cured. In our experiment, we only tested black, so we can't verify whether standard resins indeed have the same properties or if pigment significantly changes each resin's impact resistance. Another resin tested by Formlabs is Tough 2000, which has an impact strength of 79 joules per meter uncured and 40 joules per meter cured. As the name implies, Tough 2000 is an engineering grade resin that is designed to be stronger than standard resins. The last resin we tested was Elegoo water washable ceramic gray. We could not find any impact data on the Elegoo resin, and therefore this is likely the first test of its kind. Theory: to find the impact resistance of a sample, we use the change in potential energy of the hammer. This is achieved by finding the change in height of the pendulum's center of gravity before and after the sample is broken. We found the change in height using the second equation, which subtracts the sine of the initial angle by the sine of the final angle, and then multiplies the difference by the length between the pendulum center of gravity and the pendulum center or axis of rotation. Knowing the change in potential energy and the width of the sample allows us to calculate impact strength in joules per meter. To make our results more accurate, we subtracted friction losses from the change in potential energy. We'll talk more about how we measured friction losses later in the report. Test plan. Our test began with the printing and curing of 45 test specimens, which took quite a long time. These specimens were then measured to ensure their compliance with the ASTM D256-10 standard. Our test machine was then calibrated following the guidelines of the standard. To find energy loss due to friction, our test specimens were put in the vise. Once the specimen was secured, we raised the pendulum arm and the friction needle to their horizontal zero position. The arm was released, breaking the sample and moving the friction needle. The final angular position of the arm given by the friction needle was recorded. Steps 4 through 7 were repeated for the next 44 samples.
Samples and conditions tested.
We conducted impact tests on three different kinds of resin. Formlab's Tough 2000, a proprietary high tensile strength resin used for industrial and engineering applications. Formlab's black resin, used primarily by hobbyists, being that its main feature is its black color. And Elegoo water washable resin, which is also a favorite of hobbyists due to its low cost. The different UV cure conditions we subjected the resins to range from 0 minutes to 60 minutes with 15-minute increments. The impact testing machine can be seen on the left. The test is conducted as specified in our test plan. The friction needle maintains the highest angular position the arm achieved, which is then inputted into Excel to calculate the impact strength of each specimen. Calibration. To calibrate the machine, the arm was released with no specimen in the vise. The angular position reached by the arm with no specimen to break can be used in conjunction with the potential energy equation to find the energy loss due to friction in the machine. Our stand lost 0.916 joules of energy to friction. This calibration is conducted in accordance with the standard. Schedule and budget. Our schedule, as shown by the Gantt chart to the left, dedicated the first 4 weeks to our project proposal and test plan, and the next 7 weeks to print and cure test specimens, with testing beginning on week 8 and finishing on week 11. In reality, our specimens took much longer than intended to print and cure due to high traffic of 3D prints going through the makerspace. This delayed the start of our testing until week 11, but due to the rapid nature of the test, they were all completed in a single day. Our experiment was completed without a budget. All materials used were provided through the makerspace, Professor Hoover, or personal donations. Professional IZOD impact testing machines, which can be seen in the bottom right, can run in excess of $15,000, and the Formlabs resins used for testing cost $150 per bottle. To conduct a similar experiment without contributions from the makerspace and construction of our own test machine will cost an estimated $18,800. Risk assessment. The construction of our test machine required a variety of manufacturing techniques, including welding, machining, and woodworking. There are many risks associated with each of these operations, including high heat, toxic fumes, sharp blades, and many others. The 3D printing of test specimens introduced other hazards, such as VOC exposure and skin irritation. During the tests, the swinging mass creates a hazard, as well as broken specimens flying into the air. To mitigate these risks, all proper safety training and protocols put in place by the Clarkson University Student Machine Shop were followed during the construction of the test machine. Eye protection and gloves were worn while handling the 3D printer and the resin specimens, and eye protection was worn during impact testing.
Here are the results of the experiment. The ending angle of the swing arm, change in center of mass height, change in energy, and two versions of the IZOD impact energy number are listed. Each resin had its own trend with curing time, as shown in the data from the experiment. Each curing time had 3 specimens that were tested, and the average impact energy was used to represent that curing time. The average IZOD energy values for Elegoo with no cure were 31.75 joules per meter and 14.4 joules per meter for 60 minutes of cure. The average IZOD for Formlabs Black with no cure was 14.4 joules per meter, and the same for the 60-minute cure time. The average IZOD energy for no cure Tough 2000 was 70.45 joules per meter and 17.07 joules per meter for the 60-minute cure time. All the test samples demonstrated brittle fractures, with a clear trend towards more brittle fractures, following the same trend as the impact energy for each resin, such that the Tough 2000 samples become much more brittle, the Elegoo a little more brittle, and the Black not noticeably more brittle in the fracture pattern. The Tough 2000 had the most change with cure time, going from having a high impact resistance to a lower one with increased cure time. The Elegoo decreased initially but remained at about the same impact resistance after 15 minutes, and the black resin showed no relation to cure time with impact energy. The recorded IZOD value for Tough 2000 at a 60-minute cure time was 58% lower than the Formlabs number, and the no cure value was still 11% lower than the Formlabs reported value. The IZOD value for the black resin at a 60-minute cure was also 51% lower than the Formlabs reported value. This shows that we are not achieving values in line with professionally conducted experiments, rather values which give relational results between samples tested. To accurately convey data from this experiment, an uncertainty analysis was conducted to determine if the results were trustable. An RSS uncertainty analysis was used to overestimate uncertainty and give the worst case the possible uncertainty of the experiment. Any addition or subtraction means the uncertainties are added in quadrature, and any multiplication or division means the relative uncertainties are added in quadrature, as shown in the equations. The values that had uncertainty propagate from them were the angle recorded by the friction needle, the measurement of the swing arm center of mass, and the resolution of the resin printer. The standard deviation for each cure time for each resin was calculated to find the I sub r for each sample set. I sub r is the maximum allowable deviation between any two values in the data set, as listed in the ASTM value, equal to 2.83 times the standard deviation of that sample set. All of the data fell within their respective I sub r values, and the final IZOD values had an average uncertainty of plus or minus 1.94%. The results of this experiment were that two of the resins display a clear relationship between cure time and their impact strength, the Tough 2000 and the Elegoo. Due to the Formlabs resins being expired, it is also thought this played a significant role in the recorded values, being significantly lower than the published values from Formlabs. Unfortunately, since there is no data available for Elegoo resin, they could not be compared to anything known. The tanks used for the Formlab resins were also expired due to no other option being available, which may have also led to the deviance from Formlabs' value. The most effective cure times were also found for scenarios with impact strength needs. For future research into the topic, some improvements should be made. A better test stand should be made out of materials less subject to warping and expansion than wood is, as well as more rigid, and a stand with lower internal resistances. Many more samples should be used to improve data accuracy and to meet the ASTM minimum requirements of 5 samples. More types of resins could be tested, notably differing pigments, as the black resin in this test was likely less able to cure due to its pigment. The experiments could also be repeated on this test stand with FDM filaments to see if differences in their print settings can be captured in their impact energies. We would like to acknowledge Professor Hoover for his help in this experiment, the student machine shop for the machining equipment, the Dwarf Maker Space for access to the tools, printers, and resins used in this experiment, as well as Sigmund Kukla for his photographs. Thank you.
Going. Tell me when.
Yeah, go. Good.
Okay, 3, 2, 1, go. 2, 1, go.
Go ahead.
Tell me when.
Go.
3,
Zeroed
2,
out.
1, go. It's over. Go.
Oh.